Hi, my name is Tycho Collins, project leader of Group 25. In our project, we're working on AI facial generation. To kick things off with our project goals, at a high level, our mission is to build a stable, highly controllable facial generation model. The real differentiator for a model is that we want to bypass the massive enterprise server constraints that usually bottle this kind of work, engineering it to entirely run on accessible consumer hardware. So through high fidelity facial synthesis, we are implementing modern denoising diffusion probabilistic model, or in simple terms, DDPM, which is trained on a Celeb A dataset, which is a dataset of over 10,000 celebrity images. If you look back at recent history of generative AI, GANs used to be the way that facial generation and image generation were trained on. That method is unstable and difficult to train. So DDPMs give us a more robust mathematical foundation for high fidelity facial generation. This is exactly why we chose to use the new method DDPM, which was developed in 2020. So for consumer hardware optimization, the trade-off is that DDPMs require massive, expensive compute clusters. This brings us to our second and most ambitious goal, which is consumer hardware optimization. By deliberately bypassing the need for heavy enterprise servers, we're optimizing our pipeline so it can train strictly on standard setup, like everyday MacBooks and Google Colab. MacBooks and Google Colab are the hardware that we use to build our project. Since we're running on a consumer hardware, we need to look at architecture stability. Eliminating traditional collapse mode via self-attention layers and cosine beta schedule. Um, this ensures that the model actually learns the diverse underlying distribution of human faces. So finally, we have targeted attribute control. We don't just want to generate random faces. We want the output to be useful. We're developing conditional generation, which means we allow targeted attribute control. So a user could select attributes and traits like gender, skin tone, hair color, and our model will be able to generate faces matching those conditions. So ultimately, we're delivering a high fidelity controllable AI that can run on consumer hardware. And these are our project goals.
Hi, good day. My name is Damar Kenner, and we'll be going over the project requirements or constraints. So, in order to go into that, we have to first examine the essential needs, right? So, for our project, we had several key requirements that guided how we designed and built the system. First, we were we were required to use the Celeb A dataset, which contains thousands of labeled human face images. This dataset was essential because it provided both the visual data and the attribute labels needed for transitioning from an unconditional model to a conditional one. We also had to implement the entire system using Python, specifically with PyTorch. This meant building a full deep learning pipeline, including data preprocessing, model architecture, training loops, and evaluation metrics. In addition, we required to generate realistic facial images while maintaining measurable performance, which we evaluated using metrics like freshet inception distance or FID and model collapse detection. Another major requirement was expanding the original unconditional DDPM into a conditional DDPM. Initially, our model generated random faces without any control. The new requirement introduced feature-based conditioning, meaning the model had to generate faces based on selected attributes such as hair color, ethnicity, and other facial characteristics. This significantly increased the complexity of the system because we had to modify the architecture to accept and learn from both noise and attribute inputs simultaneously. In terms of constraints, one of the biggest challenges we faced was limited computational resources. Training diffusion models is very time intensive, especially on CPU and even GPU support. Training still required careful optimization to avoid long run times. Additionally, the Celeb A dataset is large, which created challenges in terms of memory usage and data handling. Another constraint was maintaining training stability. Diffusion models rely on a step-by-step denoising process, and when we introduced conditional inputs, it made the training process more sensitive. Small errors in implementation could lead to poor image quality or inconsistent future generation. Overall, while the requirements pushed us to build a complete and advanced system, the constraints forced us to be efficient, precise, and strategic in how we implemented and trained our conditional DDP model. Thank you.
Hello, my name is Eric Chavez. I'll be presenting the project design part of Group 25. So now you've seen what we needed to build and the constraints that we were working under. I want to walk you through how the system is actually designed. At the highest level, this is a four-stage diffusion pipeline. We start with the levee phase. We gradually store it with noise over 1,000 time steps, and then we train a neural network to reverse that process, to take that pure noise and walk it back into a phase. That's the core idea behind a denoising diffusion probabilistic model. The forward process is fixed. We use a linear noise schedule, and every syllabate image gets normalized into the range -1 to +1 before noise is added. There's nothing here to learn here. It's deterministic. The learn part is the denoiser. We use a UNet that takes a noisy image and a time step embedding and predicts the noise that was added. For our conditional branch, we also feed into Solid a troop labels. Things like male, eyeglasses, bald, hair color, as a learn embedding that gets concatenated in the UNet. That's what lets the user actually steer generation later into the demo. For the reverse process, we made a deliberate split. We use the standard DPM objective with MSC loss because it's stable. By inference time, we switched to DIM sampler, which lets us generate previews in seconds instead of waiting for a full 1,000 reverse chain. A few other design choices worth flagging. We capped the resolution at 64 by 64 to fit our compute budget. That was probably one of the biggest issues we have. So furthermore, like the other members talk about that furthermore. We built checkpoints and resume into the training loop, so long runs survive interruption, and we keep evaluation, FID collapse detection, in a completely separate metrics runner so it doesn't slow training down. John will now walk through all of this and see how it's implemented. Thank you so much for my part. Have a good day.
Hi, my name is John Cosby, and I'll be going over the project implementation. For the implementation of our project, we used Python and PyTorch to build our facial generation system. Initially, we worked with an unconditional DDPM model, which generates faces purely from random noise without any control over the output. We then improved our system by implementing a conditional DDPM model. This allows us to guide the generation process by selecting specific features such as hair color or ethnicity. To do this, we used attribute labels from the Celeb A dataset and incorporated them into the model as conditional inputs. So the model is trained using our train.py pipeline, and once trained, it can generate faces based on selected features instead of completely random outputs. We also integrate this into a Streamlit interface, which that allows users to interactively choose features and generate faces in real time. All generated images are stored in the outputs folder, and trained models are saved in the models directory. Thank you.
Hey, I'm Cesar Cabrera and I will cover part 5, project testing. My role focused on evaluation, metrics, and making sure the DDPM pipeline was stable, measurable, and presentation ready. The first major testing result was quantitative baseline evaluation. So during development, our original FID pipeline produced a mathematically impossible negative score, which immediately told me that the evaluation path itself was wrong. So I fixed that in metrics.py py by replacing PyTorch APath with SciPy's SQRTM so that the covariance matrix square root was handled properly. After that, I generated a proper 256 image fake evaluation set and reran the pipeline, which gave us finally a valid FID score of 80.45. The second testing area was stability. I verified that the collapse stayed false, reviewed the safe training loss behavior, and confirmed the checkpoints could be resumed correctly across long training sessions. That was very important because the model had to survive multiple runs, save states, and limited compute resources, not just work under ideal conditions. The third area was conditional functionality testing. In the conditional baseline, the model generates random faces with no feature control. In the conditional branch shown in the demo, testing focused on whether sector selected attributes such as male, female, eyeglasses, and bold were reflected in the generated faces more consistently than in the random output case. The fourth area was prototype usability. I tested the dashboard and demo workflow, the fast 50-step DDIM sampling path, and the image scaling path so the model could be shown clearly during presentation. This mattered because native model outputs are only 64 by 64 pixels, so the app needed to display them clearly and generate quickly enough for a live or recorded demo. So overall, the testing phase covered quantitative validation, long-run stability, conditional feature checks, and presentation readiness that gave us both a measured baseline and a functional demo path for the final presentation. So that concludes part 5 of project testing. Thank you for watching.
Hello, this is John Cosby again, and for our discussion, we focused on evaluating how well our system performed and what we learned throughout the project. One thing that worked really well was our ability to build a complete pipeline, from training the model to generating images and displaying them through an interface. However, we also encountered limitations, especially with diffusion models like DDPM. While they produce high quality and diverse images, they are slower and require more computational resources. We also observed trade-offs in our system. Adding feature-based control improves usability, but it can impact performance and requires more careful tuning. Compared to earlier approaches like GANs, diffusion models such as DDPM are now more widely used in modern image generation because they are more stable and produce more consistent results, even though they are slower. This is similar to how many current AI image generation systems today rely on diffusion-based models rather than GANs. So overall, this project helped us better understand how generative AI systems work in practice and showed us areas for improvement, such as optimizing performance and refining feature control. Thank you.
So this is our official demo, and for the first part of our demo, we'll be demoing our unconditional training. So our training evolution, as you can see the different epochs. At epoch 20, the faces are very blurry. This is when our model is initially learning how the faces look. So it would be scanning through the data sets and starts, running through our Celeb 8 data set 20 times. It goes through it 20 times. And you can see that while it's learning the facial structure. And through epoch 50, you start seeing more symmetry. And once you reach epoch 200, this is when you get a clear face with all the facial details, the hair strands. And so yeah, the project overview. This is, we built the DDPM model using Apple Silicon M4. And the technical specifications, we have normalization, conditional, noise scheduling, optimization. We use optimization for the weights and how our images will appear. Hardware, obviously Apple M4. So yeah, let's go right to our demo. So this is our demo for our unconditional training. This means that we generate random faces. We're not able to select which features we want. So I'm going to select 2 images, diffusion steps 1000, and submit. Okay, so the training has completed. As you see, these were the 2 faces that were generated from our conditional training. These are random faces. Alright, so this is the second part of the demo. This is where we have our unconditional training. This means that we're able to select features for our facial generation. So let's just pick male, eyeglasses, and bald. And we're going to generate our images right now. Model is generating the faces. I want to go over some of the problems, issues, and difficulties that we faced as a group during our project. And the biggest difficulty that we faced was hardware constraints. Training heavy models of facial generation takes a lot of computational power, and we were able to make it work on our hardware with our MacBooks and Google Colab. And throughout this process, the training process usually took 4 to 5 days. And when we run a training for our facial data set, our laptops, MacBooks would be overheated, and there's a term called thermal throttling, which is when your Mac overheats, it would slow down all the components and anything else you do on your Mac. So while we were training our model, we couldn't really do anything else that took a lot of computational power. Okay, so our generation is completed, and you can see that these are the 4 facial images that we generated: male, bald, and with glasses. So yeah, this will be our complete demo. In the demo, I showed you guys 2 parts: unconditional training, which generates random faces, and conditional training, where we can select features. That will be the end of our project and demo. We learned a lot as a group, and yeah, thank you so much.